There is a place in the solar system where the map quietly begins to fail. Not because nothing is there, because too much is there, and most of it is still invisible to us. For most of our lives, the solar system is drawn as a clean diagram. The Sun at the centre, the planets arranged in rings: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Then the page fades out. Maybe Pluto appears as a dot at the edge of childhood memory. Beyond that, the imagination gives up. Empty space. Cold. Dark. Finished. But that picture is not just incomplete. It is psychologically misleading. Because just beyond Neptune, around 30 times further from the Sun than Earth, the solar system does not end. It changes texture. It becomes a vast frozen archive, a broad belt of ancient bodies moving through sunlight so weak it barely deserves the name. Some are fragments. Some are the size of mountains. Some are large enough to become round worlds under their own gravity. Some carry moons. Some wear red skins made by billions of years of radiation. Some travel in calm, ancient orbits. Others move on stretched paths so strange that scientists still argue over what pushed them there. This is the Kuiper Belt. The fear about it is not that it is violent in the obvious way. It is not a storm of ice constantly smashing itself apart. It is not a science fiction minefield waiting outside Neptune. The real unease is colder. The Kuiper Belt is frightening because it reveals how little of our own solar system has actually been seen up close. We have sent machines to Mars. We have photographed Jupiter's storms, Saturn's rings, comets, asteroids, and the surface of our own moon in absurd detail. But in the Kuiper Belt, humanity has made close flybys of only a tiny handful of worlds. Pluto, once treated as the lonely last planet, turned out not to be lonely at all. Arrokoth, visited beyond Pluto, looked less like a familiar world than a surviving fingerprint from the moment planets began to assemble. That is the first rupture. The outer solar system is not a blank border. It is a museum we have barely entered. And the exhibits are not dead. Every object out there is moving. Every orbit has a history. Every tilted path. Every frozen surface. Every reddish stain is a record of something that happened before Earth had oceans, before the moon settled into its familiar place, before the solar system became the stable-looking machine we trust today. The Kuiper Belt sits far enough from the Sun that ordinary intuition starts breaking down. At Earth, sunlight feels immediate and powerful. It warms skin, it drives weather, it grows forests. Beyond Neptune, it becomes a thin grey memory. The Sun is still the gravitational centre of everything, but it no longer feels like the blazing star that rules our days. It becomes distant, small, severe. On some of those frozen bodies, water ice is not soft, temporary, or fragile. It behaves like rock. Methane, nitrogen, carbon monoxide, substances we know as gases or unstable materials in everyday life, can sit frozen into the ground for eons. Chemistry does not stop, but it slows until time itself seems to thicken. Cosmic rays strike the surface, molecules break and recombine. Over millions and billions of years, simple ices darken into complex organic compounds. A world that looks inert from far away may be quietly manufacturing chemistry on its skin, one particle impact at a time. Cold does not mean nothing is happening. It means change has moved on to a timescale we are not built to feel. The Kuiper Belt forces us to think in clocks that do not belong to human life. Pluto takes 248 Earth years to circle the Sun. Arrokoth takes hundreds. Sedna, one of the strangest distant objects ever found, follows an orbit so long that a single year there lasts more than 10,000 years on Earth. A civilization could rise, write its myths, build its cities, collapse into dust, and Sedna would still be on the same slow curve through darkness. That kind of time does something to the mind. It makes the solar system feel less like a place and more like a memory that has not finished unfolding. And this is where the story becomes more dangerous. Because the Kuiper Belt is not only an archive of what survived, it is also a record of what was lost. The region we see today is not the original outer solar system. Scientists think the early outer disk was far more massive, packed with icy bodies before the giant planets shifted into their modern arrangement. In leading models, Neptune migrated outward, scattering icy objects as it moved, throwing some into stable resonances, flinging others into wild orbits, and sending many either inward toward the young planets or outward into exile. So when we look at the Kuiper Belt, we are not looking at a complete structure. We are looking at wreckage that learned how to look calm. That distinction matters. A stable orbit can be the end result of a violent past. A quiet, frozen object can be a survivor of gravitational chaos. A comet that appears in the night sky can be a fragment from that distant population, nudged inward after millions of years in the dark, carrying ice and organics older than Earth's surface. The same region that may have helped deliver some of Earth's early water and organic chemistry may also have contributed to ancient bombardments that scarred the inner solar system. The same frozen bodies that preserve the ingredients of beginnings can become impactors. Creation and destruction can come from the same reservoir. That is why the title is not just a dramatic phrase. The Kuiper Belt is far more terrifying than most people are told, because it does not frighten us like an approaching object frightens us. It frightens us by removing the comfort of the familiar map. It shows that the solar system was not built as a clean set of planets in permanent order. It was negotiated. It was scattered. It was rearranged by gravity, collision, migration, and chance. And the evidence is still out there, circling in the dark beyond Neptune. What makes the next step stranger is that the Kuiper Belt was not first understood by seeing it clearly. It was inferred. Before telescopes revealed the population, scientists noticed that something did not add up. Comets kept returning. They lost material whenever they passed near the Sun. They could not survive forever. If they were still appearing after billions of years, they had to be coming from somewhere. There had to be a reservoir, a hidden supply, a cold storage zone beyond the known planets, feeding the inner solar system with ancient ice. For years, that idea was not a photograph. It was a pressure in the math, a missing answer, a shadow cast by objects that had not yet been seen. And then, in 1992, astronomers found the first small body beyond Pluto that made the belt undeniable. One faint object, one moving point of light. Not impressive to the eye, but scientifically, it was a door opening. Because if one was there, then many more had to be there. And once astronomers began looking carefully, the clean edge of the solar system dissolved. More objects appeared, then more. Then enough to make Pluto look less like the last planet and more like one bright member of a much larger, stranger population. That was the moment the old diagram truly began to die. Neptune was not the edge. Pluto was not alone. And the darkness beyond them was not empty. It was crowded with frozen witnesses. And those witnesses changed the shape of the solar system in a way almost nobody was ready to accept. At first, the discovery beyond Pluto seemed small. A faint object, catalogued as 1992 QB1, was not the kind of thing that could rewrite a child's poster. It was not bright. It was not famous. It did not have a heart-shaped plane or a moon large enough to make headlines. It was simply there, moving slowly against the background stars, following the sun from a distance where no planet was supposed to be waiting. But in astronomy, one object in the right place is never only one object. It is evidence of a population. If a telescope finds a single faint body in a narrow patch of sky, then the reasonable question is not why that one exists. The question is how many similar bodies were missed because the sky is large, the objects are dark, and our instruments had not been looking deeply enough for long enough. Within years, more bodies appeared, then hundreds, then thousands. The region beyond Neptune stopped being an afterthought and became a field of study. The clean diagram was not missing a dot. It was missing a whole province. And Pluto, The object everyone thought they understood was suddenly standing in a crowd. That is what made Pluto's later reclassification so emotionally painful and scientifically important. In public memory, Pluto's demotion felt like a loss. A beloved little planet had been taken away. People reacted as if a familiar place had been erased from the solar system. But science was not erasing Pluto. It was finally giving Pluto its proper neighborhood. For decades, Pluto had looked lonely because we could not see what surrounded it. It sat at the edge of the known map, small, cold, eccentric, tilted, and strange. Those strangenesses were treated as personal quirks. Pluto had an odd orbit. Pluto was unusually small. Pluto crossed inside Neptune's distance during part of its path. Pluto did not behave like the other outer planets. But because it stood alone in the diagram, people accepted the exception. Then the Kuiper Belt filled in around it. Once that happened, Pluto's oddness became less like a flaw and more like a clue. It was not a tiny failed version of Jupiter, Saturn, Uranus, or Neptune. It was one of the largest known members of a different family entirely. Icy worlds beyond Neptune, shaped by cold, resonance, collision, migration, and survival. The emotional story was that Pluto had lost status. The scientific story was that Pluto had gained context. That context became impossible to ignore when astronomers discovered Eris, another distant world similar enough to Pluto to force a decision. If Pluto was a planet, then Eris had a strong claim too. And if Eris was included, then other large Kuiper Belt objects would follow. The old category could stretch until it lost meaning, or the category itself had to be rebuilt. This is why the Pluto debate mattered more than the word planet. It exposed a deeper problem. Human categories often come from what we notice first, not from what nature is actually doing. We saw Pluto before we saw its population, so we gave it a name that fit our ignorance. Then the ignorance shrank, and the name began to strain. The Kuiper Belt did not merely add objects to the solar system. It changed the meaning of an object we already knew. That is one of the most unsettling things science can do. It can take something familiar and not destroy it, but relocate it inside a larger truth. Pluto did not become less real. It became more specific, less mythic perhaps, but more revealing. A world with mountains of water ice, plains of nitrogen, a thin atmosphere, a system of moons, and a place inside a vast architecture of frozen bodies. And that architecture is not random. Some Kuiper Belt objects move in relatively calm, stable orbits. These are often called classical objects, and many of them may have remained in the outer solar system for billions of years, with comparatively little disturbance. They are not untouched in a perfect sense, because nothing in space is truly untouched. Radiation works on their surfaces, small impacts happen, gravity never stops. But compared with the restless inner solar system, they are close to preserved. Others are locked in orbital resonances with Neptune. Resonance is one of those words that can sound gentle until you understand what it means. It is gravity turned into rhythm. An object completes a certain number of orbits for every certain number made by Neptune, and that timing can protect it from dangerous close encounters. Pluto is in a 3-to-2 resonance with Neptune. For every 3 orbits Neptune makes, Pluto makes 2. Their paths cross in distance but not in timing. The rhythm keeps them apart. There is something almost musical about that. But it is not music. It is survival mathematics. A small world can remain safe for billions of years because its motion falls into a pattern that avoids catastrophe. Shift the timing, and the same orbit might become unstable. A world that looks secure is secure only because the invisible arithmetic of gravity has not failed. Then there are the scattered objects. These are the bodies that carry the more obvious scars. Their orbits are stretched, tilted, and unsettled, often shaped by past encounters with Neptune or by the early migration of the giant planets. They are the thrown stones of the outer solar system. Some move far beyond the main belt before falling back toward the region of Neptune. Some may eventually become comets, Some may be sent inward. Some may be lost entirely. The more scientists studied these different families, the clearer it became that the Kuiper Belt is not one simple ring. It is layered history, a calm population, a resonant population, a scattered population, a set of survivors sorted by a long gravitational violence we can no longer watch directly, only reconstruct from the positions of bodies still moving today. That is the strange power of the outer solar system. It keeps records without writing them down. A tilted orbit is a scar, a resonance is a shelter, a red surface is a clock, a missing mass is a crime scene, and a dwarf planet is not a demotion when it becomes evidence that the map was wrong. This is where the Kuiper Belt becomes more than a remote collection of ice. It becomes a test of how much history can be hidden inside motion. We look at a small point of light drifting across a telescope image, and if we measure patiently enough, that point begins to speak. Its color tells us about radiation, its brightness hints at size, its path reveals gravity, its tilt carries memory, its companions reveal mass, its surface may preserve chemistry older than Earth. Nothing out there explains itself quickly. Everything has to be inferred from fragments. That is why the region feels so severe. The Kuiper Belt does not give us the comfort of close inspection. It gives us hints, and the hints are enough to show that the outer solar system is not a quiet edge, but a structured remnant of an earlier, rougher reality. And once Pluto was placed inside that remnant, the next question became unavoidable. If Pluto was not alone, and Eris was not alone, and thousands of smaller bodies were not alone, then what exactly were these frozen worlds made of? What had they preserved for 4.5 billion years? And why did so many of them wear that dark red colour, as if the edge of the solar system had been slowly stained by time itself? The red colour is not decoration. It is damage turned into evidence. Across the Kuiper Belt, many objects reflect light in a way that looks unusually red, sometimes so red that scientists describe the surface as ultra-red. That colour does not come from rust in the ordinary Earth sense. There is no air out there, no rain, no oxygen-rich weather patiently corroding stone. The redness is built by radiation working on ice in darkness for spans of time the human mind can barely hold. Start with a surface made of simple frozen substances: water ice, methane ice, nitrogen ice, carbon monoxide, carbon dioxide. Materials that behave like gases or liquids in warmer places can become solid at Kuiper Belt temperatures, locked into crusts and mantles beneath a distant sun. Then imagine cosmic rays arriving from beyond the solar system, high-energy particles moving through interstellar space, striking those surfaces again and again for billions of years. Each impact is tiny, but time makes tiny things enormous. A particle hits a molecule and breaks a bond. The pieces recombine. Simple carbon-bearing ices become more complex compounds. Those compounds darken. They redden. They form materials known broadly as tholins, organic rich residues that can coat an icy world like a slow chemical stain. The process is not fast. It is not dramatic. Nothing explodes. Nothing glows. The surface simply absorbs time until time has a colour. That is why the red worlds of the Kuiper Belt feel so different from bright planets closer to the Sun. Their colour is not weather in the familiar sense. It is exposure. It is the visible result of being left alone in cold radiation long enough for chemistry to become a historical record. A fresh, icy surface would look brighter. A surface recently scraped by an impact might expose cleaner material underneath. But a stable object, quietly orbiting in the classical belt, can keep the same outer skin long enough for radiation to write across it for nearly the full age of the solar system. The redder the surface, the more it can suggest a long period of relative calm. Not safety, exactly. Space is never safe, but enough stillness for the slowest processes to accumulate. This is one of the strange reversals of the Kuiper Belt. The bodies that look dead may be the best witnesses. On Earth, activity destroys memory. Plate tectonics drags crust into the mantle. Volcanoes cover old surfaces. Rivers grind stone into sediment. Wind erases. Ice carves. Life itself transforms the chemical face of the planet. Earth is alive, and because it is alive, it is constantly forgetting its earliest surface. The Kuiper Belt does the opposite. It preserves by doing almost nothing. Its worlds are not perfectly unchanged, but they are closer to the beginning than almost anything we can touch. They formed from the same broad disk of gas and dust that built the planets. Then many of them remained far from the heat and violence that remodeled the inner solar system. Their surfaces became cold storage. Their interiors may still contain mixtures of ice, rock, and trapped volatile compounds that date back to the earliest stages of planet formation. That makes them scientifically priceless. A Kuiper Belt object is not just an object. It is a sample of the solar system before the solar system became familiar. And the chemistry locked inside those bodies raises one of the deepest questions in planetary science. How much of Earth's beginning came from somewhere else? The question sounds almost poetic until it becomes chemical. Comets that enter the inner solar system carry water ice, carbon compounds, dust, and sometimes amino acids or related organic molecules. Some of these comets are linked to distant icy reservoirs, including the scattered populations connected with the Kuiper Belt. When they approach the Sun, their frozen surfaces begin to sublimate. Solid ice turns directly into gas. Jets lift dust into space. A coma forms around the nucleus. A tail stretches outward, pushed by sunlight and solar wind. To the eye, a comet looks like a visitor. To chemistry, it is a delivery system. The material streaming from a comet may have been frozen since before Earth was fully formed. It may contain compounds assembled in darkness, altered by radiation, preserved in cold, and then released into sunlight after billions of years. When such bodies struck the early Earth, they did not arrive gently. They arrived with enormous energy. They blasted craters. They vaporized rock. They helped make the young planet a violent place. But impacts can destroy and deliver at the same time. Some of Earth's water may have come from icy bodies in the outer solar system, though the exact contribution is still debated. Some of the organic ingredients useful for prebiotic chemistry may also have arrived from space. Scientists do not need to claim that life itself fell intact from the Kuiper Belt. That would go far beyond what the evidence can safely support. The stronger and more serious idea is more subtle. The early Earth may have received part of its chemical starting kit from ancient icy bodies formed far from the Sun. That is enough. It means the boundary between Earth and the outer solar system is not as clean as the diagram suggests. The ocean, the atmosphere, the first carbon chemistry, the early molecular pathways toward life. All of these may have been shaped in part by objects that began in the dark beyond Neptune or in related outer reservoirs. The terrifying part is not that the Kuiper Belt is trying to harm us. It is that we may be connected to it more intimately than we want to admit. A frozen object 4 billion miles away can look irrelevant until it becomes a comet. A comet can look like a spectacle until it becomes an impact. An impact can look like destruction until it leaves behind water, carbon, nitrogen, and molecular possibility. The same body can be a weapon and a seed. The same reservoir can threaten a planet and help make it habitable. This is why the Kuiper Belt resists simple emotion. It is not only beautiful, it is not only dangerous. It is older than those categories. It belongs to a time when the solar system was still sorting itself, when the ingredients of worlds were being scattered, merged, frozen, broken, and redirected. And because the belt preserved so much of that early material, it also preserved the evidence of a missing solar system. Not missing in the sense of a hidden civilization or a secret planet waiting in every shadow, but missing in the more profound scientific sense. The original outer disk was much larger than the thin remnant we see today. Most of its material is gone. That loss is not a detail. It is the next fracture in the story. If the Kuiper Belt is only what survived, then the real question is no longer simply what is out there now. The real question is what happened to everything that vanished. The The vanished material is one of the quietest mysteries in the solar system. Not because scientists have no explanation, because the explanation makes the solar system feel less permanent than it looks. Today, the Kuiper Belt contains far less mass than early models suggest it should. There are many objects there, but together they amount to only a thin remnant compared with the original disk of icy material that likely surrounded the young sun beyond the giant planets. In some reconstructions, that ancient outer disk contained tens of Earth masses of material. Today, the known Kuiper Belt holds only a small fraction of one Earth mass. That is not a minor loss. That is the difference between a rich construction zone and a nearly emptied ruin. Something removed most of the material, and the main suspect is not a collision, not a passing catastrophe, not a single explosion in the dark. It is gravity, working through the slow rearrangement of giant planets. The early solar system did not begin in the arrangement we see now. The planets were not placed into final lanes like beads on a wire. They formed inside a disk, interacted with leftover material, pulled on one another, and migrated. Jupiter, Saturn, Uranus, and Neptune shaped the disk around them. But the disk also shaped them. Every small icy body carried a little momentum. Every gravitational encounter exchanged a little energy. Over millions of years, those exchanges added up. Neptune appears to have moved outward. That one sentence is simple enough to miss. But if Neptune migrated outward through the original outer disk, then it did not merely travel through space. It ploughed through a population. It disturbed orbits. It captured some objects into resonances. It scattered others outward into long, unstable paths. It threw some inward toward the giant planets. It may have helped send waves of icy bodies into the inner solar system. It erased much of the original architecture and left behind a belt that looks stable only because the most unstable material is already gone. The Kuiper Belt we see today is not the untouched edge of the solar system. It is what remained after Neptune passed through. This is why orbital families matter so much. A resonance is not only a mathematical curiosity. It can be a fossil of migration. When Pluto orbits in a 3-2 rhythm with Neptune, that rhythm may carry memory of the era when Neptune moved outward and swept objects into protected patterns. Other bodies were not so lucky. They were pushed into chaotic trajectories or removed entirely. The giant planets did not simply decorate the outer solar system. They edited it. One of the leading frameworks for this history is often called the Nice model, named after the city in France where major work on it was developed. The details are still tested and debated, and no model should be treated as a final photograph of the past. But the broad idea is powerful. The giant planets once occupied a more compact arrangement, then shifted into new orbits as gravitational interactions with the leftover planetesimal disk changed their motion. In some versions of this story, Jupiter moved slightly inward, while Saturn, Uranus, and Neptune moved outward. Neptune's outward movement destabilized the outer disk, scattering icy bodies across the solar system. Some were driven into the Kuiper Belt families we observe now. Some were sent into the scattered disk. Some were flung toward the inner planets. Some escaped the sun entirely and became interstellar wanderers. That last possibility changes the scale of the loss. The missing Kuiper Belt is not merely missing from our telescopes. Much of it may no longer belong to the solar system at all. Imagine an icy body formed near the young sun, in the same broad birth environment that produced the planets. It circles for millions of years inside a dense outer disk. Then Neptune's gravity alters its path. Uranus pulls. Saturn contributes. Jupiter finishes the exchange. The object gains enough energy to leave. The sun's grip weakens, then breaks. The frozen fragment begins a one-way journey into interstellar space. It does not explode. It does not announce its departure. It simply stops coming back. If enough objects took that route, the galaxy may be filled with exiles from planetary systems like ours. Frozen pieces of old formation disks, drifting between stars after being thrown away during the violent youth of their own systems. Interstellar visitors show that planetary systems can exchange debris with the galaxy. What left our system may resemble what enters from others. The edge of one solar system can become the debris field of another. This makes the Kuiper Belt feel less like a border and more like a survivor's ledger. Each object still there has a reason it was not removed. Its orbit avoided the worst scattering. Its resonance protected it. Its distance saved it. Its timing happened to be right. What we call the belt is a selected population, filtered by ancient chaos. And that ancient filtering may have mattered for Earth. During the early instability of the giant planets, some icy objects were likely sent inward. The inner solar system already carried scars from bombardment, visible most clearly on the Moon, where there is no atmosphere or active geology to erase the record quickly. Whether every detail of the timing is settled or not, the larger truth remains severe. The early solar system experienced intense impact activity, and the outer reservoirs of icy bodies were part of the supply chain. A fragment thrown from the outer disk could become a comet. A comet could cross the inner solar system. Some would miss. Some would be captured into shorter period orbits. Some would strike planets. In the violence of impact, they could deliver water, carbon compounds, and other materials, while also releasing enough energy to reshape a surface. Again, the double nature returns. The same rearrangement that made the modern Kuiper Belt may have helped shape the conditions on early Earth. The same scattering that emptied the outer disk may have fed the inner planets with ancient ice. The same violence that threatened young worlds may have contributed to the chemistry that later made them habitable. This is not a comforting kind of order. It is not the tidy order of a machine designed from the beginning. It is the order left after instability has done its work. The solar system became stable by losing material. It became familiar by surviving a period when familiar arrangements were not guaranteed. That realization bends the emotional meaning of the Kuiper Belt. It is not just far away. It is evidence that the current solar system is a result, not a promise. Neptune could have migrated differently. The resonances could have captured a different population. More material could have been thrown inward. Earth could have been struck more heavily or spared key ingredients. The arrangement we now call normal may be only one outcome among many that were physically possible. The Kuiper Belt holds that possibility in silence. Every remaining object is both a relic and an accusation. It says the solar system used to contain more. It says the giant planets moved. It says small worlds were scattered, exiled, broken, preserved, or redirected. It says stability may be something a system earns only after it has thrown away most of its dangerous options. And beyond the survivors of Neptune's migration, there are objects that do not fit the story cleanly at all. They sit too far out. They avoid Neptune too completely. Their orbits seem to remember a force larger than the machinery of the Kuiper Belt. One of them is Sedna, and the outer solar system became stranger than the model that had just explained it. Sedna did not arrive like a dramatic image. It arrived like a problem. When astronomers discovered it in 2003, they were not seeing a world up close. They were seeing a faint, moving point against the fixed background of stars. But the motion was wrong in the most important way. It was slow, distant, and placed in a region where ordinary Kuiper Belt behavior could not easily explain it. Sedna's closest approach to the Sun is already far beyond Neptune. That detail matters more than its size, more than its color, more than the fact that it is one of the largest known bodies in the distant solar system. Neptune can sculpt the Kuiper Belt. Neptune can trap objects in resonances, scatter them into wild paths, and send some inward as future comets. But Sedna stays too far away for Neptune to be the simple answer. It does not come close enough. That is why Sedna felt like a message from outside the machinery scientists had just begun to understand. Its orbit is enormous. It takes more than 11,000 Earth years to circle the Sun once. At its farthest distance, it moves into darkness so deep that sunlight needs days to reach it. The Sun from there would not look like the ruler of a warm planetary system. It would look like a brilliant star. Important because gravity remembers what light can barely express. A year on, Sedna is longer than recorded human history. That single fact is not just a scale comparison. It changes the emotional meaning of an orbit. When Sedna last occupied some parts of its path, no human city existed. No empire had risen. No writing system had recorded a name. And when it returns there again, everything we consider modern may be as distant from the future as the Stone Age is from us. Sedna moves through a clock that makes civilization feel like weather. But the real puzzle is not how long it takes. The real puzzle is who placed it there. Standard Kuiper Belt dynamics cannot easily lift an object into Sedna's detached orbit. It belongs to a population sometimes described as detached, because its path is separated from the main gravitational reach of Neptune. It is not a normal classical Kuiper Belt object. It is not simply a scattered disk body returning again and again to Neptune's neighbourhood. It seems to occupy a middle wilderness between the known belt and the even more distant theoretical reservoir of icy bodies called the Oort cloud. That middle zone should not have been crowded with large objects, according to the older, simpler map. Sedna proved the map was still too small. Scientists proposed several possibilities. One is that another star passed near the young sun when the solar system was still embedded in its birth cluster. Stars are not fixed, they move around the galaxy, and young stars often form in crowded nurseries, where close gravitational encounters are more likely than they are in the sun's current quiet neighbourhood. A passing star could have tugged at the outer solar system, lifting distant icy bodies into elongated orbits that Neptune alone could never create. If that happened, Sedna is not merely a body, it is a scar left by another star. Another possibility is that the sun's birth environment itself shaped the outermost objects. The early solar system may have formed among many neighbouring stars, with collective gravitational effects stirring the distant disk before the sun drifted away from its siblings. Under this view, Sedna remembers not one clean encounter, but the crowded place where the solar system was born. A third possibility points back into the present darkness. An undiscovered planet, massive enough and distant enough to shepherd objects over billions of years, could help explain Sedna-like orbits. This is where the idea of Planet 9 enters the story, but it has to be handled carefully. It is not confirmed. No telescope has photographed it. No instrument has directly measured its light. It remains a hypothesis built from orbital patterns, simulations, and the difficulty of explaining certain distant objects without another source of gravity. That uncertainty is not a weakness in the story. It is the story. The outer solar system has entered a region where scientists can see effects more clearly than causes. They can measure an orbit. They can model possible histories. They can eliminate explanations that fail. But the final source remains unresolved. Sedna may be the signature of a stellar flyby. It may be a survivor of the sun's birth cluster. It may be part of a population shaped by an unseen planet. It may require some combination of histories we have not fully untangled yet. The frightening part is not that scientists have no ideas. It is that several serious ideas are still possible. Sedna widened the solar system without moving anything. It simply forced our concept of the edge to expand. The Kuiper Belt was already larger than the schoolbook diagram. The scattered disk pushed beyond that. Sedna pushed beyond the scattered disk. And beyond Sedna lies the Oort cloud, a vast theoretical shell of icy bodies, extending so far from the sun that the boundary between solar system and interstellar space becomes more like a fading influence than a wall. The farther out we go, the less the solar system looks like a neat disk. It starts to look like a gravitational atmosphere, a zone of belonging that thins gradually into the galaxy. That is why Sedna matters so much. It stands near the transition between the solar system we have mapped and the solar system we infer. It tells us the sun's control extends farther than our direct knowledge. It tells us ancient events can leave orbital evidence that survives for billions of years. It tells us the outer edge is not a line, but a memory field. And it also changes the emotional role of darkness. Darkness is not just the absence of sunlight. In the outer solar system, darkness is where evidence hides until motion reveals it. A body too faint to study can still betray itself by its path. A planet too distant to see, if it exists, can still leave fingerprints in the motion of smaller worlds. A passing star long gone from the Sun's neighbourhood can still be suspected because something in the deep cold refuses to orbit the way it should. Sedna is that refusal. It is a small red witness to a force we have not fully named, and once one detached object existed, the question could not remain isolated. If Sedna was there, then others might be there. If others were there, their orbits might form patterns, and if those patterns were real, then the outer solar system might be shaped by something still unseen, still massive, still waiting in the dark beyond the belt. The darkness beyond the belt does not need to contain a monster to become disturbing. It only needs to contain a pattern. That is where the idea of Planet 9 becomes so powerful, and so dangerous to handle carelessly. The phrase sounds almost too clean, as if a missing world has already been found and only waits for a camera to catch up. But the science is not there yet. Planet 9 is not a confirmed planet. It is a proposed explanation, a gravitational suspect, a way of making sense of certain distant orbits that appear too organized to ignore and too faintly sampled to trust completely. This is the tension at the heart of the search. The evidence is not a photograph. It is geometry. Some of the most distant known objects beyond Neptune follow long, stretched orbits. A few of those orbits seem to cluster in orientation, as if their paths have been arranged by a slow, persistent gravitational influence. In simulations, a massive planet far beyond the Kuiper Belt could help produce that kind of clustering. It would not need to be bright. It would not need to come anywhere near the familiar planets. It could orbit so far from the Sun that 1 year on that world would last thousands or even tens of thousands of Earth years. A planet like that, if real, would change the emotional size of the solar system. Neptune would no longer feel like the last major world. Pluto would no longer feel like a sentimental boundary. The Kuiper Belt would no longer be the outer neighbourhood, but part of a larger gravitational story whose strongest actor had remained unseen. But there is a second possibility, and it is just as important. The pattern may not be a planet. It may be the shape of our own ignorance. Astronomy is not a perfect act of looking everywhere equally. Telescopes observe certain parts of the sky more often than others. Surveys have limits. Weather matters. Telescope location matters. The brightness of an object matters. The background stars matter. The season of observation matters. A distant Kuiper Belt object must be in the right place, at the right brightness, moving slowly enough to identify, against a sky that has been examined with the right instrument at the right time. That means the objects we know are not necessarily a fair sample of all the objects that exist. They are the objects our methods were able to find. This is where the Planet 9 debate becomes more intellectually interesting than simple mystery. One side says the clustering is real enough to demand a massive, distant perturber. Another side argues that observational bias may be creating the appearance of clustering from incomplete data. Both positions are serious. Both are rooted in attempts to protect the truth from wishful thinking. The disagreement is not between believers and skeptics in the cheap sense. It is between different ways of asking how much pattern a limited dataset can honestly support. That is a more mature kind of suspense. Not, is there a hidden planet? But, how do you know when the universe is showing you a real structure, and when your instruments have drawn one for you? This question reaches far beyond Planet 9. It sits inside all frontier science. At the boundary of detection, reality and method become entangled. The telescope does not only reveal the universe, it also filters it. Every survey has a shape. Every instrument has blind spots. Every dataset carries the imprint of how it was collected. When scientists look into the distant solar system, they are not staring into a complete inventory. They are building one faint moving dot at a time. And every missing dot matters. If Planet 9 exists, it is likely cold, dark, and remote. It may be several times the mass of Earth. It may follow an elongated orbit hundreds of times farther from the Sun than Earth. At those distances, sunlight is so weak that even a large planet would reflect only a trace of light back toward us. It might sit against dense star fields. It might move so slowly across the sky that years of observations are needed to distinguish it from background objects. Finding it would be less like spotting a planet and more like noticing that one nearly invisible point has shifted when almost everything else has not. That is why absence is not simple. Not finding it yet does not prove it is not there. But not finding it also means the hypothesis must remain provisional. This restraint is what makes the subject stronger, not weaker. A dishonest version of the story would declare the planet real, turn every strange orbit into proof, and use darkness as permission to invent certainty. A better version keeps the unease intact. Either there is a major undiscovered planet shaping distant bodies, or the outer solar system is teaching us a severe lesson about bias, small numbers, and the danger of seeing order too soon. Both outcomes are unsettling. In the first, our own solar system still contains a massive world we have not seen. In the second, our confidence in the pattern was partly built by the limits of our looking. Either way, the familiar map loses authority. The search has practical urgency, because new surveys can change the debate. Wide-field telescopes, deeper sky surveys, and long-term tracking of faint objects may reveal more distant bodies with Sedna-like orbits. If the clustering strengthens as the sample grows, the case for an unseen planet becomes harder to dismiss. If the clustering dissolves, then Planet 9 may fade into the long history of elegant ideas that helped science sharpen its methods before disappearing. That is not failure. That is how the edge of knowledge behaves. It offers shapes before it offers certainty. And while the Planet 9 debate continues, the Kuiper Belt remains strange enough without it. Neptune's migration still emptied the ancient disk. Pluto still breathes through its thin atmosphere. Arrokoth still preserves the gentle early sticking of planetesimals. Sedna still follows an orbit that Neptune cannot easily explain. Comets still arrive from deep reservoirs, carrying old ice into sunlight. None of that depends on a confirmed ninth planet. The terror is not hanging on one hypothesis. It is distributed through the whole architecture. The outer solar system is a place where incomplete evidence is still powerful, where a faint object can reopen the past, where a missing planet may or may not exist, and where the difference between discovery and illusion depends on patience, humility, and better data. So the darkness beyond the Kuiper Belt is not empty in the simple sense. It is crowded with possibility. And possibility is not a soft thing in science. It demands discipline. It punishes overconfidence. It waits for instruments strong enough to separate what is real from what only looked real because we had not yet seen enough. And while scientists search for the source of those distant patterns, another kind of evidence has already arrived from the belt itself, not as a hypothesis, not as a point of light, but as images from a spacecraft that actually crossed the boundary and showed us what one of these frozen worlds looks like when the blur becomes a landscape. The first landscape did not arrive all at once. It came across billions of miles as a signal so weak that the distance itself seemed to be speaking. New Horizons had left Earth in January 2006, moving faster than any spacecraft ever launched at the time. It crossed the orbit of the Moon in hours, reached Jupiter in a little over a year, stole speed from the giant planet's gravity, and kept falling outward into a part of the solar system no machine had ever visited. Even at that speed, Pluto was nearly a decade away. That is the first thing the flyby teaches before any image appears. The Kuiper Belt is not merely far, it is operationally brutal. Distance becomes engineering. Distance becomes delay. Distance becomes silence. A command sent from Earth takes hours to reach the spacecraft. A signal sent back takes hours to return. During the closest approach, there was no real-time steering, no human hand correcting the moment as it happened. New Horizons had to perform its encounter almost alone, following instructions loaded in advance, pointing its instruments with extreme precision while racing past Pluto at more than 30,000 miles per hour. It could not stop. It could not orbit. It had one chance. For decades, Pluto had been a smudge. Even the best telescopes had given scientists only hints: patches of light and dark, a large moon, evidence of volatile ices, a thin atmosphere. People argued about what Pluto was while barely knowing what Pluto looked like. Then, in July 2015, the blur became a world. The images did not make Pluto simpler. They made it more alive. There were mountains, real mountains, rising from the surface. But they were not made of ordinary rock. At Pluto's temperature, water ice is rigid enough to behave like stone, strong enough to hold up peaks. There were plains of nitrogen ice, smooth and pale, broken into strange polygonal cells that suggested slow internal motion. There were dark terrains, bright terrains, cratered regions, young surfaces, and a vast heart-shaped basin that turned a distant dwarf planet into one of the most recognizable worlds in the solar system. That heart was not sentimental. It was geology. The bright region, now known as Tombau Regio, contains a broad plain called Sputnik Planitia, a basin filled with nitrogen ice. On Earth, nitrogen is a gas that makes up most of the air. On Pluto, it becomes a moving, frozen landscape. It can sublimate into the atmosphere, refreeze on the surface, and flow slowly under its own weight. The movement is not fast enough for a human to watch, but planetary surfaces do not need human speed to be active. Over thousands and millions of years, frozen nitrogen can behave like a glacier made from air. That phrase should feel wrong. A glacier made from air. But Pluto is a place where familiar substances have been pushed into unfamiliar roles. Water becomes bedrock. Nitrogen becomes ice. Methane becomes frost. Sunlight becomes a seasonal suggestion. A world smaller than Earth's moon, sitting at the inner edge of the Kuiper Belt, turns out to have cycles, textures, and histories that no simple category can hold. The most unsettling question was not what New Horizons saw. It was what powered it. Pluto is far from the Sun. It is small. It has no obvious source of strong tidal heating, like some moons around Jupiter or Saturn. Yet parts of its surface appeared surprisingly young. Craters were missing, where old craters should have accumulated. Plains seemed to be renewing themselves. Possible cryovolcanic features hinted that material from below may have reached the surface in the past. Some models even allow for a subsurface ocean, buried under a shell of ice, kept from freezing completely by a combination of internal heat, insulating layers, and the complex physics of ice. That possibility remains an area of active study. It should not be turned into a claim that Pluto is secretly alive or habitable in any ordinary sense. But even the possibility matters. It means that liquid water, or at least long-lived internal activity, may not be confined to worlds close to the Sun or moons squeezed by giant planets. The boundary between dead and active is not where intuition wanted to place it. Pluto did not behave like a frozen corpse. It behaved like a small world with a complicated interior, and its atmosphere made the picture stranger. New Horizons photographed blue haze layers stacked above Pluto's limb. Delicate bands of particles formed as sunlight interacted with methane and nitrogen high above the surface. The atmosphere is thin, far thinner than Earth's, but it is real. It expands and changes with Pluto's long seasons. Volatile ices move between ground and air. The surface and atmosphere speak to each other in a slow exchange, not over days and storms, but over years, decades, and centuries. Again, the same lesson returns. Cold does not mean still. It means the clock is different. Pluto's large moon, Charon, deepened the shock. Charon is so large compared with Pluto that the two bodies orbit a point in space outside Pluto itself. They are not quite a planet and an ordinary moon in the familiar emotional sense. They are closer to a double world, tidally locked, facing each other across a fixed gravitational relationship. From one hemisphere of Pluto, Charon would hang in the same part of the sky and never set. From the other, it would never rise. Charon had its own violence written across it. Vast canyons, fractured terrain, a dark reddish polar cap likely built from chemistry that began with material escaping Pluto. Even the companion world was not simple. The Pluto system was not a lonely dot. It was a miniature architecture of ice, atmosphere, moons, and exchanged material at the threshold of the Kuiper Belt. This is why the flyby mattered beyond public fascination. It proved that the edge could not be judged from blur. Before New Horizons, Pluto could be made small by language. Dwarf planet, former planet, Kuiper Belt object, remote body. Those labels are useful, but they can become emotionally flattening. They can make a world feel settled before it has been seen. The spacecraft broke that flattening. It showed that even a small, icy body in deep cold can carry landscapes as specific and strange as any planet. And then New Horizons kept going. It had no way to break after Pluto. Its path carried it deeper into the Kuiper Belt, away from the world that had transformed from a point into a place. Scientists searched for another target, something small enough and far enough to preserve even older information. They found Arrokoth, a faint object nearly invisible from Earth, waiting more than 1 billion miles beyond Pluto. If Pluto showed that the Kuiper Belt could contain active worlds, Arrokoth would show something quieter and in some ways more profound. Not what happens after a world becomes complex. What happens before a world has fully become a world at all? Arrokoth looked almost too simple to be important. That was the trap. When New Horizons reached it on January 1st, 2019, the spacecraft was farther from Earth than Pluto had been, flying through a region where the Sun was already a distant point of light, and every radio signal had to crawl back across more than 4 billion miles. The target was tiny compared with Pluto, only about 22 miles long. From Earth, it had been little more than a faint dot, discovered by careful telescope work. No one expected mountains, atmosphere, glaciers, or dramatic geology. And Arrokoth did not offer any of that. It offered something older. The first clear images showed a strange two-lobed shape, like two flattened, rounded bodies gently joined at a narrow neck. People compared it to a snowman, then to a pancake pear, then to a contact binary. But the casual comparisons could hide the scientific force of what New Horizons had seen. Arrokoth was not a broken piece of a larger world. It was not a fragment obviously shattered from a violent collision. It appeared to be two small planetesimals that had formed near each other, drifted together slowly, and touched with such low speed that they merged without destroying themselves. That kind of contact is a fossil. Not a fossil of life, but a fossil of assembly. For decades, planetary scientists had tried to understand how dust and ice in the young solar system became larger bodies. The basic outline seems simple. Small things stick, grow, collide, merge, and eventually build planets. But the details are difficult. If collisions are too fast, bodies shatter instead of grow. If the disk is too turbulent, gentle assembly becomes hard to maintain. If the early stages cannot be explained, the whole story of planet formation has a missing step. Arrokoth gave that missing step a shape. Its lobes suggested that, at least in some regions of the outer solar system, early growth could be delicate. Not soft in the emotional sense, not peaceful in any human moral sense, but dynamically gentle. Two small bodies could settle into the same gravitational neighborhood, lose relative speed, spiral together, and join without a catastrophic impact. The result was a single object preserving the moment before larger worlds were built. That is why Arrokoth matters so much more than its size. A mountain-sized object beyond Pluto can tell us how planets began. Its surface deepened the story. Arrokoth is red, coloured by the same broad family of radiation-processed organic material found on many outer solar system bodies. It has no obvious atmosphere, no strong internal heat, no active weather. Its shape and surface suggest that it has remained relatively undisturbed since the earliest age of the solar system. It is not exciting because it is active. It is exciting because it may be quiet enough to remember. Pluto showed that the Kuiper Belt can surprise us with complexity. Arrokoth showed that simplicity can be just as revealing. The two worlds sit inside the same larger region, but they answer different questions. Pluto asks what an icy dwarf world can become after billions of years of internal evolution, volatile cycles, atmosphere, and interaction with moons. Arrokoth asks what the building blocks looked like before that evolution had time to erase the original form. One is a landscape, the other is a construction clue. Together, they dismantle the idea that small, distant bodies are scientifically minor. A world does not need to be large to be fundamental. Sometimes the smallest preserved object carries the oldest information. This is the reason scientists want more Kuiper Belt flybys, more distant surveys, more patient tracking of faint bodies. Telescopes can measure brightness, colour, and orbit. They can infer size and composition, but a spacecraft changes the relationship. It turns a point into a surface. It reveals texture, shape, craters, layering, brightness variation, and geometry that no distant observation can fully resolve. The problem is that spacecraft do not move at the speed of curiosity. They move at the speed of engineering. To reach Pluto, New Horizons needed 9.5 years. To reach Arrokoth, it needed several more. Its trajectory had to be planned years in advance. Its target had to fall within a narrow cone of reachable space. Its instruments had to function in deep cold, using limited power, sending information home through a signal weaker than almost anything human technology regularly depends on. Even after the flyby, the data did not arrive all at once. It trickled back slowly, as if the Kuiper Belt made us wait to understand what we had touched. That delay is part of the region's terror. The Kuiper Belt is close enough to belong to our solar system, but far enough to resist possession. We can calculate it, we can name parts of it, we can classify populations and draw orbital diagrams. But actual contact is rare, expensive, slow, and partial. Each flyby feels less like exploration of a familiar neighbourhood and more like a brief interception of deep time. And Arrokoth added a further discomfort. If an object this small, this faint, this easily ignored, could transform our understanding of planet formation, then how much knowledge is still hidden in bodies we have never seen clearly at all? The answer is almost certainly enormous. The Kuiper Belt contains many objects larger than Arrokoth, and countless smaller ones. Some preserve ancient surfaces, some have been altered by impacts, some belong to resonances that remember Neptune's migration, some drift in the scattered disk on paths that may one day feed comets inward. Some may be binary pairs, two small worlds orbiting each other in mutual gravity. Some may hold compositions that differ from anything New Horizons has sampled. We have not visited them. We have barely introduced ourselves. This changes how Arrokoth should be remembered. It is not an endpoint of exploration. It is a warning against confidence. Before the flyby, scientists could model early planetesimal formation. After the flyby, they had a preserved object testing those models in physical form. One small red body became a judge of theories built on Earth. That is what the Kuiper Belt keeps doing. It takes ideas that seem settled from a distance and makes them answer to objects in the dark. Pluto forced categories to bend. Arrokoth forced formation models to sharpen. Sedna forced Neptune's influence to show its limits. The Planet 9 debate forces scientists to ask whether distant patterns are real or partly made by the way we observe. Each object is not just a thing, it is an argument, and the arguments are not finished. Because beyond the few worlds we have seen up close lies a population where some objects do not travel alone. They move with companions, orbiting shared centres of mass, preserving clues about density, collision history, and the gentle or violent ways small bodies can become pairs. In the darkness beyond Neptune, even a moon can stop being ordinary. A moon, in the familiar imagination, belongs to something large. Earth has one. Mars has two small captured-looking companions. Jupiter and Saturn carry whole systems of moons, some of them large enough to feel like planets in their own right. A moon seems to imply a major body, a central world with enough gravity to hold smaller objects around it. The Kuiper Belt complicates that instinct. Out beyond Neptune, many small icy bodies have companions. Some are simple moon systems, with one body clearly larger and another smaller object circling it. But others are stranger. They are binaries, paired worlds close enough in size that the word moon begins to feel misleading. Instead of one object dominating and the other merely following, the two bodies orbit a shared center of mass, a point that may lie in the empty space between them. That detail matters because it turns a pair of faint dots into a measuring instrument. When scientists observe two Kuiper Belt objects orbiting each other, they can calculate the mass of the system from the timing and shape of the orbit. Mass is otherwise difficult to measure for distant bodies. Brightness can mislead because a small bright object may reflect as much light as a larger dark one. Size estimates depend on assumptions about reflectivity, but orbital motion gives something more solid. Gravity tells the truth in a language of time. A binary system is not only a curiosity, it is a scale, and the existence of so many binaries tells us something about the environment where they formed. Some pairs may have come from capture, where one object passed close enough to another for gravity to bind them together. But capture is difficult unless energy can be lost from the encounter. Two objects approaching each other too quickly will usually meet, bend paths, and separate again. To become a long-term pair, they need the right speed, the right geometry, and often the presence of a third body or a broader cloud of material to carry away excess energy. Another possibility is more elegant. Many binaries may have formed together, born from the same local concentration of material in the young outer disk. If particles and pebbles collapsed into two nearby clumps instead of one, the pair would naturally share a similar orbit around the Sun and a low relative speed. Binding would be easier. Their partnership would not be an accident after formation, but part of formation itself. The Kuiper Belt may preserve those early partnerships better than the inner solar system could. Closer to the Sun, higher speeds, stronger heating, more frequent encounters, and planetary gravity can disrupt fragile systems. But in the cold outer disk, a pair formed gently might survive for billions of years. Two small worlds can keep circling one another in darkness, a quiet binary clock ticking since before Earth had a crust stable enough to remember itself. That kind of survival is not sentimental. It is evidence. It suggests the early outer solar system was not only violent, it contained pockets of extraordinary gentleness, places where small bodies could assemble slowly, pair off, and remain bound. This is what makes the Kuiper Belt so hard to reduce to a single mood. The same region records scattering, impact, migration, and exile. Yet it also preserves contact binaries like Arrokoth, and paired worlds that may have formed through delicate processes. The outer solar system was not one thing. It was a field where violence and quiet construction happened at the same time. The most famous binary-like relationship in the Kuiper Belt is Pluto and Charon. Charon is usually called Pluto's largest moon, and technically that language is acceptable, but it does not capture the strangeness of the system. Charon is enormous compared with Pluto, roughly half Pluto's diameter. That proportion is unlike the relationship between Earth and its moon, where the moon is much smaller relative to Earth. Pluto and Charon are close enough in size and mass that they orbit a barycenter outside Pluto's surface. In plain language, Pluto does not simply sit still while Charon goes around it. Both bodies circle a shared point in empty space. This makes the system feel less like a planet and moon, and more like a double world. They are also tidally locked to each other. The same face of Pluto always turns toward Charon, and the same face of Charon always turns toward Pluto. If you stood on the hemisphere of Pluto that faces Charon, you would not see it rise or set. It would hang in one region of the sky, fixed by orbital rhythm, a large grey companion suspended above the horizon. Stand on the far side of Pluto, and Charon would never appear at all. The sky itself would depend on which side of the world you were born on. Charon's surface tells its own history. New Horizons revealed a world marked by fractures, canyons, smoother plains, darker regions, and a reddish polar cap. The Great Canyon system suggests that Charon's interior may once have expanded as internal water froze, cracking the crust from within. The red polar region appears linked to material escaping from Pluto, then settling onto Charon and being transformed by radiation into darker, organic-rich compounds. Even their surfaces are not entirely separate. Pluto loses material, Charon receives some of it, radiation changes it. Over time, a relationship becomes a stain visible from space. That is the kind of detail that makes the outer solar system feel intimate in spite of its distance. Two frozen worlds locked face to face, exchanging material across empty space, carrying the memory of formation, internal change, and chemical processing in their surfaces. Not dead objects, not simple objects, not background debris. A small system with a biography, and once you see Pluto and Charon this way, the word belt starts to feel inadequate. A belt sounds like a ring of loose material, a simple outer band. But the Kuiper Belt contains worlds with moons, binaries, atmospheres, resonances, scars, organic chemistry, and histories that reach back to the first architecture of the solar system. It is not a ring of leftovers. It is a population of unfinished biographies. Some of those biographies are quiet. Some are violently disturbed. Some are paired. Some are solitary. Some have surfaces that may have remained undisturbed for billions of years. Some have been stripped, stained, fractured, or pushed onto extreme paths. Together they form a record no single spacecraft can read. And yet the record keeps sending pieces inward. That is where the story turns back toward Earth. Because the Kuiper Belt is not sealed behind Neptune. It leaks. Through collisions, resonances, and gravitational nudges, some icy bodies leave the outer darkness and begin long falls toward the Sun. For most of their existence, they are invisible, frozen, and remote. Then sunlight reaches them strongly enough to wake their surfaces. A frozen witness becomes a comet, and what looks beautiful in the night sky is the Kuiper Belt burning off its ancient skin. The tail is not smoke. It is memory becoming visible. For billions of years, a small icy body can move through the outer solar system without looking like anything special. It is dark, cold, and nearly inert, circling in a region where sunlight is too weak to do much more than mark the direction of the Sun. Its surface may be coated in processed organics. Its interior may preserve water ice, carbon compounds, carbon monoxide, methane, ammonia, and dust from the earliest disk that surrounded the young star. Then something changes. A gravitational nudge shifts the orbit. It may come from Neptune. It may come from a resonance that slowly destabilizes the path. It may come after a collision that changes velocity by a tiny amount, not enough to look dramatic at the moment, but enough over long time to send the object inward. The path stretches. The frozen body begins to fall towards stronger sunlight. For a long time, nothing obvious happens. Then the surface begins to wake. At first, the most volatile ices respond. Materials that were stable in the deep cold begin to sublimate, changing directly from solid to gas. Gas escapes through cracks and weak points, lifting dust away from the surface. Jets form. A cloud grows around the nucleus. This cloud, called the coma, can become vastly larger than the solid body itself. The nucleus may be only a few miles wide, but its atmosphere of escaping material can swell across tens of thousands of miles. A comet is not really a dirty snowball in the childish sense. It is a small, ancient world losing itself in public. As it comes closer to the Sun, sunlight and solar winds shape the escaping material into tails. One tail is dust, curved by the comet's motion along its orbit. Another is ionized gas, pushed more directly away from the Sun by charged particles streaming through space. The result is the beautiful form humans have feared, worshipped, recorded, and misunderstood for thousands of years. a bright visitor with a luminous train across the night sky. But the beauty is a kind of erosion. Every glowing tail is material being stripped from an old body. Every pass near the sun removes part of the comet. It cannot do this forever. After enough returns, the ices are depleted. The surface changes. The object may fragment, fade, or become a dark, exhausted remnant. The comet is temporary because the inner solar system is hostile to the chemistry that preserved it. That is why returning comets require a source. They must be supplied from colder reservoirs. Short-period comets, the ones that return on timescales under 200 years, are strongly linked to the outer solar system populations associated with the Kuiper Belt and scattered disk. They are not random decorations. They are evidence that the deep cold is dynamically connected to the warm inner regions. The belt leaks through gravity. It sends old ice inward. It turns preserved material into visible spectacle. And sometimes the spectacle intersects a planet. This is where the emotional meaning of comets becomes difficult. They can be beautiful from a distance and catastrophic on contact. A body only a few miles across, moving at tens of thousands of miles per hour, carries enough kinetic energy to alter climate, excavate crust, throw dust into the atmosphere, and change the trajectory of life. Impact is physics without intention. It does not hate. It does not aim in the human sense. It simply follows a path. And if Earth occupies the same point at the same time, the sky becomes geology. The early Earth lived under a much heavier version of that sky. The young inner solar system was struck far more often than it is today. The Moon still carries much of that record because it lacks the same active weather, oceans, and plate tectonics that erase Earth's scars. Craters remain there like a fossilized bombardment map. Some of that impact history is tied to leftover material from planet formation, including icy bodies destabilized as the giant planets migrated and the outer disk was rearranged. So the Kuiper Belt is not safely distant in the deep time sense. Its fragments helped write the history of the inner solar system. They may have brought destruction. They may also have brought ingredients. Water. Carbon-bearing molecules. Nitrogen-bearing chemistry. Simple organics that could become part of the prebiotic inventory on a young planet. The evidence does not require the strongest form of panspermia, the idea that life itself travelled intact between worlds. The more cautious and powerful idea is that life's raw materials are not unique to Earth. They can form in space. They can survive in ice. They can be delivered by impact. That changes the feeling of a comet completely. It is not only an omen. It is not only a threat. It is a courier from the solar system's formation era. When scientists analyze comet dust, they are not simply studying debris. They are reading chemistry that may predate the final assembly of Earth. Sample return missions and close comet studies have shown that these bodies can contain complex organic material and amino acid-related chemistry, the kinds of compounds that matter because biology uses carbon chemistry with extraordinary precision. Again, caution matters. Finding useful molecules is not the same as finding life. But it shows that some of the steps toward biological chemistry can happen before there is a living planet to host them. The beginning of life may not have required Earth to invent every ingredient alone. That is a profound shift. The ocean may carry a history larger than the ocean. This is why comets produce such a strange double vision. They can end worlds. They may help begin them. And the source region beyond Neptune carries both possibilities at once. The same ancient ice that preserves organic chemistry can arrive with catastrophic speed. The same distant reservoir that stores early solar system material can become a delivery system into planetary atmospheres. The same darkness that protects a molecule for billions of years can release it violently when gravity changes the path. Nothing in this story is morally clean. The Kuiper Belt is not benevolent because it may have contributed ingredients to Earth. It is not malevolent because some fragments can strike planets. It is older than moral categories. It is a physical reservoir, governed by gravity, radiation, cold, and time. Its terror comes from that indifference. It gives and destroys without knowing the difference. And even now, most of its smaller bodies remain unseen. That ignorance matters. Large objects are easier to find. Small dark bodies are not. A distant object reflects only faint sunlight, and the light has to travel back across billions of miles before reaching our telescopes. Many objects capable of becoming comets may remain below detection limits until their orbits bring them closer to the Sun and their surfaces begin to brighten. By the time some visitors reveal themselves, they are already on their way in. The night sky makes comets look brief. The Kuiper Belt makes them ancient. And once that connection is clear, the belt stops being a distant ring and becomes a breathing boundary between preservation and arrival, between the deep freeze of the solar system's beginning and the bright, destructive warmth near the Sun. But comets are only the objects that leave. The ones that remain out there, frozen in place or locked in slow orbits, hold another secret. Some of them are not merely icy fragments, but worlds with seasons, atmospheres, and weather so slow that a human lifetime would barely notice it passing. Weather, in the outer solar system, almost stops being weather, not because it disappears, because it becomes too slow for our instincts. On Earth, weather is immediate. Clouds gather in hours, rain falls by evening, winds shift while people are still standing outside. The atmosphere is restless, noisy, thick enough to press against skin, and powerful enough to turn oceans, forests, and deserts into living systems of exchange. We understand weather as movement because we live inside movement. But on a Kuiper Belt world, the atmosphere can be so thin, so cold, and so seasonal that it behaves less like air and more like a temporary state of ice. Pluto is the clearest example we have seen up close. It should have been easy, from a distance, to imagine Pluto as frozen beyond activity, a small body, billions of miles from the Sun, receiving only a fraction of Earth's sunlight, should not feel meteorologically alive. Yet New Horizons found a world with a real atmosphere, thin but structured, mostly nitrogen with traces of methane and carbon monoxide. It found blue haze layers rising above the surface, delicate bands of particles suspended in a sky so faint that calling it a sky already stretches the word. The atmosphere is not stable in the comforting way Earth's is stable. It depends on the long breathing of Pluto's orbit and seasons. Pluto moves around the Sun in 248 Earth years, and its path is not a neat circle. Sometimes it comes closer, sometimes it moves farther away. The difference changes how much sunlight reaches the surface, and in a place this cold, a small change in sunlight can decide whether nitrogen stays frozen on the ground or lifts into gas. So Pluto's atmosphere can grow and shrink over time. It can partially collapse. It can refreeze onto the surface. A planet's sky can fall down. That sentence sounds like fantasy until the physics becomes clear. At Pluto's temperatures, nitrogen is not safely gaseous. It is near the boundary between surface ice and atmosphere. When conditions allow, it sublimates upward. When conditions change, it freezes back. The line between ground and air becomes negotiable. What we think of as atmosphere is not a permanent blanket, but a seasonal exchange, a slow circulation between surface and sky. This is not weather as humans experience it. It is planetary breathing, measured in decades. That same idea may apply to other large Kuiper Belt objects and related distant worlds. Eris, for example, is far more distant for much of its orbit, and its volatile ices may spend long ages locked to the surface. When it comes closer to the Sun, some of those ices may become more active, perhaps allowing a thin, temporary atmosphere to appear. Makemake shows signs of volatile material and surface complexity. Triton, Neptune's large moon, is not a Kuiper Belt object now, but many scientists think it may have originated from the same distant population before Neptune captured it. It has nitrogen geysers, a thin atmosphere, and a surface that reminds us how active cold worlds can be when the right energy source exists. The outer solar system keeps breaking the simple rule that distance means death. Distance changes the mechanisms. It does not erase them. On Earth, the sun drives weather directly. In the Kuiper Belt, the sun is weak, but weak does not mean absent. A little sunlight, spread across long seasonal cycles, can still move volatile ices. Internal heat may matter. Impacts may expose fresh material. Radiation may alter surfaces. Gravity from moons may shape rotations and histories. The activity is quieter, colder, slower, but it exists. This is why Pluto was such a shock. It did not merely have features. It had relationships. Surface and atmosphere, ice and gas, sunlight and season. Pluto and Charon, interior and crust, chemistry and haze. Nothing about it fit the lazy idea of a dead ice ball. And if Pluto could surprise us that much, then every large Kuiper Belt body becomes suspicious. What is Haumea doing with its rapid spin and elongated shape? What histories are locked inside its icy fragments and family? What does Makemake's surface preserve under its methane and complex coloration? What does Eris look like during the long, cold stretch of its orbit, when the sun is so distant that its surface may hold atmosphere as frost for centuries? How many smaller worlds have seasonal behavior too subtle for us to detect from Earth? These are not decorative questions. They are reminders that a telescope's silence is not the same as a world's stillness. From far away, an object can look unchanged because our measurements are too crude, our time baseline too short, or our instruments too far from the truth. A season lasting a century can hide inside a human career. A surface process unfolding over 10 million years can look frozen to a civilization that has only been using telescopes for a few centuries. The outer solar system does not need to be inactive to appear inactive. It only needs to move at speeds beneath our patience. That is one of the hardest lessons of the Kuiper Belt. Human attention is short. Planetary time is not. A haze layer can form molecule by molecule. A surface can redden grain by grain. A volatile ice field can shift across centuries. A binary pair can turn face to face through billions of locked rotations. A distant orbit can carry a world from relative sunlight to near total darkness and back again, while entire civilizations appear and vanish on Earth. When we call such places dead, we may simply be confessing the limits of our tempo. The terror here is subtle. It is not the terror of impact or hidden mass or a possible planet waiting beyond the survey maps. It is the terror of realizing that activity does not require our scale. The universe can be dynamic while looking still. It can be chemically alive without being biological. It can keep time in such vast measures that our instruments see only a single frame and mistake it for permanence. The Kuiper Belt is full of single frames, a dot of light with a color, a slow orbit, a brightness change, a hint of methane, a possible moon, a shape inferred from a stellar occultation, a temperature too cold to feel real. From these fragments, scientists reconstruct worlds. But reconstruction is not possession. The more we learn, the more the unknown becomes specific. We no longer say only that the outer solar system is mysterious. We can name the mysteries. Seasonal atmospheres, red organic surfaces, detached orbits, contact binaries, missing mass, possible hidden perturbers, comet delivery pathways, ancient planetesimals preserved in deep cold. The darkness becomes organized. And an organized darkness is more unsettling than a vague one, because once the unknown has structure, it begins to make demands. It asks for better telescopes. It asks for longer surveys. It asks for spacecraft that may not arrive until the people who designed them are old. It asks us to accept that the solar system we live in is not the tidy, finished diagram, but a layered machine whose outer mechanisms are still partly concealed. And the concealment is not only about what is far away, it is also about what is too small, too dark, and too numerous to count. The smallest objects may be the most important ones we cannot see. A large Kuiper Belt world announces itself, at least faintly. Pluto was found because it was bright enough to move against the stars. Eris, Makemake, Haumea, Sedna, and other distant bodies were detected because they reflected enough sunlight for careful surveys to notice them. Even then, they appeared first as points, not places. Their true nature had to be inferred through orbit, brightness, colour, occultation, and patience. But below a certain size, the belt becomes nearly invisible. This is not because the objects are rare. It is because distance punishes light twice. A Kuiper Belt object receives weak sunlight in the first place. At 40 times Earth's distance from the Sun, the light is already more than 1,000 times dimmer than it is here. The object reflects only a fraction of that light, depending on how dark its surface is. Then that reflected light has to travel all the way back across the same vast distance to reach a telescope near Earth. By the time it arrives, the signal can be so faint that the object effectively disappears into the background. A dark body a few miles wide can be real, ancient, chemically rich, dynamically dangerous, and still beyond detection. That should bother us. Not because every hidden object is an immediate threat. Most are not. The distances are enormous. The probabilities on human timescales are low. But the unseen population carries the missing statistics of the Kuiper Belt. Without it, we do not fully know the collision history. We do not fully know the size distribution. We do not fully know how often small bodies are produced, broken, scattered, or sent inward. We are trying to understand a population while seeing mostly its larger bones. Imagine reconstructing a forest after being allowed to count only the oldest trees. You would know something true, but not enough. The small objects are the seeds, splinters, fragments, and survivors that reveal how the whole system grinds over time. Their numbers tell scientists whether collisions were common or rare. Their sizes tell us how planetesimals formed. Their colours reveal whether surfaces were refreshed or left exposed. Their orbits show which pathways gravity uses to move material from the outer cold into the inner solar system. The Kuiper Belt is not just missing worlds. It is missing data at the scale where history becomes statistical. This is why new surveys matter so much. Wide-field observatories can scan large portions of the sky again and again, looking for faint points that shift slightly against the background stars. The key is repetition. A distant object may not look impressive in a single image. It may be nearly indistinguishable from noise, but across multiple nights, its slow motion betrays it. Stars hold their positions relative to one another. Solar system bodies drift. Motion is the confession. Future and current deep surveys will not make the Kuiper Belt fully known overnight. The region is too large, the objects too faint, and the orbits too slow for any simple inventory. But they can change the nature of the unknown. They can reveal more detached objects like Sedna, testing whether its orbit is rare or part of a larger population. They can find more distant bodies whose alignments strengthen or weaken the case for an unseen planet. They can measure the distribution of smaller objects more precisely. They can show whether our current sample has been biased by where and how we looked. This last point is crucial. At the edge of detection, a catalogue is never only a catalogue of what exists. It is also a catalogue of what our tools were capable of finding. If a survey favours certain regions of the sky, certain brightness ranges, or certain orbital positions, the population it discovers will carry those preferences like fingerprints. A cluster of objects might be real, or it might be partly produced by the way the search was conducted. A gap might be physical, or it might be observational. A distant world might be absent, or it might be waiting in a patch of sky not yet examined deeply enough. The Kuiper Belt forces science to be humble because the evidence is sparse and expensive. You cannot walk the terrain. You cannot send hundreds of probes. You cannot watch a full orbit of most objects because their years last centuries or millennia. You build truth from partial arcs. A few years of motion across a human telescope baseline must be used to infer an orbit that may take thousands of years to complete. That is a profound act of mathematical trust, It works because gravity is lawful, but it remains dependent on measurement, assumptions, and time. More observations shrink uncertainty. Fewer observations leave ghosts. This is why the outer solar system feels different from the inner one. Mars can be mapped in global detail. The Moon can be measured down to boulders. Jupiter's moons can be revisited, compared, targeted, and imaged. But the Kuiper Belt is still mostly an inferred landscape. It is a region where names arrive long before details, and details arrive only after years of patient refinement. A point becomes an orbit becomes a category becomes a theory of history, and sometimes a spacecraft must cross billions of miles to check whether the theory had the right shape. That is the discipline the Kuiper Belt demands. It punishes overstatement, but it also punishes complacency. If we say too much, we turn darkness into fantasy. If we say too little, we miss the fact that the darkness already contains structure, chemistry, motion, and clues to our own beginning. The honest position is harder and more interesting. We know enough to be unsettled. We do not know enough to be comfortable. Somewhere beyond Neptune, countless bodies are moving tonight without names. Some are probably small fragments from ancient collisions. Some may be pristine planetesimals never warmed enough to change. Some may be future comets, still frozen on long paths that will one day bring them inward. Some may be binaries too faint to separate. Some may belong to populations we have not yet recognized because the first examples have not yet crossed our instruments clearly enough. The solar system still has an undiscovered texture, and the most frightening part is not that a single object is hiding there. It is that the hiding is systematic. The physics of distance, darkness, size, and time all work together to keep the Kuiper Belt partly concealed. Not maliciously, not mysteriously in the cheap sense, simply because the universe has no obligation to make its evidence convenient. So the next revolution may not come from one dramatic discovery. It may come from accumulation, hundreds of faint points, thousands of measured arcs, patterns that slowly sharpen, biases that slowly disappear, a belt that slowly becomes less imaginary and more populated, less mythical and more severe. And as the inventory grows, one question will become harder to avoid. If this much has remained hidden in our own solar system, orbiting the same sun that lights our days, what else have we mistaken for emptiness, simply because we have not yet learned how to see it? If emptiness can hide this much, then the problem is not only astronomical. It is perceptual. Human beings are bad at emptiness. We look at a gap and treat it as absence. We look at darkness and treat it as nothing. We look past the last familiar object and assume the story has run out. That instinct may work on a table, a road, a room, or a shoreline. It fails in space, where distance can dilute a crowded region until it looks blank, and where a population of worlds can disappear behind the weakness of reflected light. The Kuiper Belt is not empty in the way the diagram once suggested. It is empty in the way a deep ocean is empty when seen from an aeroplane. The surface looks smooth because the observer is too far away. That difference is everything. From Earth, the outer solar system is reduced to faint points and calculated paths. But inside that vastness, the physical reality is specific. A red surface faces a dim sun. A binary pair turns through darkness. A slab of nitrogen ice waits through a season longer than empires. A small body holds organic-rich material under a crust aged by radiation. A detached object crawls through an orbit that remembers a force no one has fully identified. None of this looks dramatic from here. That is what makes it dangerous to understanding. The most important realities are not always the loudest. A supernova announces itself across galaxies. A storm on Jupiter can be seen through a telescope. Saturn's rings glitter with obvious structure. But the Kuiper Belt works differently. Its truths are dim, slow, cold, and statistical. They do not shout. They accumulate. A color measurement, a missing crater, a strange tilt, A resonance. A faint occultation when a distant body passes in front of a star. A slow drift across images taken nights apart. From these fragments, scientists assemble the outer solar system's hidden architecture. The process is almost the opposite of spectacle. It requires patience, skepticism, and an ability to let small evidence become large only when it has earned the right. The Kuiper Belt is terrifying precisely because it cannot be conquered by one glance. It makes certainty expensive, and that expense should change how the whole solar system feels. The inner planets give us the illusion of possession. We can send orbiters. We can map craters. We can track weather. We can land rovers and drill into rock. The more detail we gain, the more the place seems to enter human scale. Mars becomes a landscape. The Moon becomes a terrain of named sites and mission paths. Even the giant planets, impossible to stand on, become visually familiar through repeated images. But beyond Neptune, familiarity collapses. The objects are too distant for frequent return. The missions are too long for easy repetition. The targets are too many for one spacecraft. The light is too faint for simple seeing. The orbits are too slow for complete watching. We are not exploring a neighborhood in the ordinary sense. We are intercepting rare clues from a territory that mostly continues without us. That humbles the idea of home, because this is not another star system. This is ours. The sun that holds Earth also holds the Kuiper Belt. The same gravity that keeps our planet in its year also keeps Sedna on its vast loop and Arrokoth on its quiet path. The same early disk that produced Earth also produced those red frozen bodies beyond Neptune. The same history that arranged the inner planets scattered and preserved the outer debris. The Kuiper Belt is not alien because it is separate. It is alien because it is connected to us and still almost unknown. That connection matters emotionally. If the Kuiper Belt were around another star, its mysteries would feel remote, almost abstract. But it belongs to the same system as our oceans, our seasons, our moon, our atmosphere, our history of impacts, and possibly some of our earliest chemical ingredients. It is not outside our story. It is the part of our story that remained cold enough to keep the receipts. That image is severe. A frozen ledger beyond Neptune. A record of the solar system's youth preserved in bodies too dim to see well. And the ledger is incomplete. Some pages were thrown into interstellar space. Some burned away as comets. Some struck planets. Some remain locked in resonances. Some are hidden by darkness. Some may never be visited by any spacecraft humans build. Yet together, they form one of the most honest archives we have. Not an archive made for us, not one arranged for understanding. A physical archive, indifferent and scattered, where every object is a surviving document. This is why the Kuiper Belt becomes more unsettling the more accurately we describe it. The exaggerated version is less frightening. A fake story about a forbidden planet or impossible physics can shock for a moment, then collapse because it has no foundation. The real version lasts longer. It says there are billions of ancient bodies beyond Neptune. It says we have seen almost none of them up close. It says some preserve chemistry from the birth of the solar system. It says some are dynamically linked to comets. It says some orbits may remember migrations, stellar encounters, or unseen gravitational influences. It says the solar system still contains a history we cannot fully read. No invention is needed. The truth is already deep enough, and the truth has a final pressure inside it. The Kuiper Belt is not only about the past, it is also about the future of discovery. Every new survey, every occultation, every improved model, every distant flyby has the power to move the edge again. Not the physical edge, but the edge in the mind. The point where the known gives way to the inferred. The point where a dot becomes a world. The point where empty becomes populated. That edge has moved before. It moved when Pluto was discovered. It moved when 1992 QB1 confirmed the belt. It moved when Eris forced the planet category to break. It moved when new horizons revealed Pluto's mountains and haze. It moved when Arrokoth showed a preserved planetesimal. It moved when Sedna refused Neptune's explanation. It may move again when the next generation of surveys finds dozens or hundreds of distant objects that redraw the patterns we argue over now. The solar system is still becoming visible. Not because it is changing quickly, because our seeing is, it has always been, larger than the picture we carried. And as our seeing changes, the old emptiness does not disappear. It gets corrected. That correction is never gentle. Every time a deeper instrument looks outward, the solar system becomes less like the simple structure we inherited and more like a layered record of events we were not present to witness. The familiar planets remain, but they stop being the whole story. Neptune stops being a final wall. Pluto stops being a lonely exception. The Kuiper Belt stops being a distant ring of leftovers and becomes a frontier where categories, histories, and assumptions keep failing in useful ways. This is why the next era matters so much. The future of Kuiper Belt science will not be built only by one heroic spacecraft flying past one more object, although that would be priceless. It will also be built by surveys that watch the sky repeatedly, patiently, almost monotonously, until faint moving points begin to multiply. The drama will not always look dramatic. It may come as a catalogue, a database, a statistical shift, a cluster that becomes stronger, a cluster that dissolves, a new detached object that makes Sedna seem less lonely, a new population that had been hiding below the old brightness limits. Discovery, out there, may arrive as accumulation. That sounds less cinematic than a single shocking image, but it may be more powerful. A single object can change a model. A population can change a worldview. If future surveys reveal many more Sedna-like bodies, then the outer solar system will need a stronger explanation for how they were placed there. If the apparent orbital clustering behind the Planet 9 hypothesis fades with a larger and less biased sample, then science will have learned something equally important. The edge of knowledge can create false shapes when the data are thin. If the clustering becomes sharper, the pressure for a real distant perturber will grow. Either way, the darkness will give something back. That is the discipline of this frontier. It does not allow only the exciting answer. It allows the answer the evidence can survive. Sometimes that answer is a new world. Sometimes it is a removed illusion. Sometimes the most important discovery is that a beautiful pattern was never real. That may sound disappointing, but it is one of the deepest forms of progress. Science does not only find things, it learns how not to fool itself. The Kuiper Belt is a perfect place for that lesson, because it sits at the boundary between seeing and inference. We cannot stand on most of its worlds. We cannot watch complete orbits. We cannot easily send missions wherever curiosity points. We have to reason from light, motion, colour, temperature, occultations, and rare encounters. Every conclusion has to carry the weight of uncertainty honestly. Every dramatic claim has to be tested against the possibility that the universe is not being mysterious. Our sample is simply incomplete. That humility makes the subject stronger, because the real Kuiper Belt does not need exaggeration. It already contains a former planet that turned into the key to a larger population. It contains red worlds whose surfaces have been chemically altered by cosmic radiation since the beginning of the solar system. It contains paired bodies orbiting shared centers of mass. It contains ancient fragments that become comets. It contains dwarf planets with volatile ices, slow seasons, and possible hidden interiors. It contains detached objects whose orbits may remember stellar encounters, planetary migration, or gravitational influences we have not yet confirmed. It contains enough truth to make fiction unnecessary. The question is how far we are willing to follow that truth. A spacecraft mission to another Kuiper Belt object would require patience almost alien to modern life. Years of planning, years of travel, instruments that must survive deep cold and limited power, a trajectory that must be chosen with extreme care because fuel is scarce and the distances leave little room for second chances. The reward might be a few hours of close observation after a journey lasting a decade or more, then years of analysis, years of data moving slowly back through space. That is what it costs to turn one dot into one world. And yet the cost is worth it, because every dot that becomes a world has so far made the solar system stranger, not simpler. Pluto did. Arrokoth did. Even distant bodies never visited, like Sedna and Eris, change the architecture from afar. The pattern is clear enough to be humbling. The outer solar system has repeatedly punished our expectation that small, cold, distant objects must be simple. They are not simple. They are quiet. That difference may be the central lesson of the entire journey. Quiet worlds can still have histories. Quiet surfaces can still hold chemistry. Quiet orbits can still reveal violence. Quiet darkness can still contain structure. What appears inactive may be active on a timescale too large for us. What appears empty may be populated at a distance too great for our eyes. What appears settled may only be settled because we stopped asking questions too early. The Kuiper Belt is not frightening because it overturns physics. It is frightening because it obeys physics so completely that human intuition cannot keep up. Gravity moves bodies for billions of years. Radiation builds chemistry one broken bond at a time. Cold preserves what heat would erase. Distance hides what proximity would reveal. Time turns small nudges into different destinies. None of this is supernatural. None of it is impossible. That is exactly why it lingers. The universe does not have to break its rules to become disturbing. It only has to follow them farther than our minds are comfortable going. And beyond the belt, the structure continues fading outward. The scattered disk stretches into more extreme orbits. Detached objects mark a middle realm still poorly understood. Farther still, the Oort cloud may surround the solar system like a vast, loose halo of icy bodies, so distant that passing stars and the galaxy's tide can disturb them. At that scale, the sun's ownership becomes faint but not gone. The solar system no longer feels like a set of rings. It feels like a field of influence thinning into interstellar space. A home with no sharp wall. A boundary made of gravity becoming weaker. That is where the Kuiper Belt leaves us before the final turn. It stands between the familiar planetary system and the almost unimaginable outer reservoirs beyond. It is close enough to be part of our map, and distant enough to prove the map is still unfinished. It preserves beginnings, supplies comets, challenges categories, records migration, and hides populations we have not counted. It is the first place where the solar system stops behaving like an illustration and starts behaving like an ancient, damaged, still unread archive. And once you understand that, the fear becomes clearer. The terrifying thing is not one object. It is not Pluto, not Eris, not Sedna, not Planet 9 if it exists, not a comet falling inward from the dark. The terrifying thing is the realization that our own solar system still contains regions where the most honest statement is not "we know," but we are learning how little the old picture knew. The old picture knew almost nothing about the place where it chose to stop. That is the thought that remains after Neptune, after Pluto, after Arrokoth, after Sedna, after all the faint bodies whose names most people will never hear. The schoolbook map was not malicious. It was not foolish. It was simply young. It drew a boundary where instruments, categories, and imagination ran out. It made the solar system look finished, because unfinished things are hard to print cleanly on a page. But the real solar system was never clean. It was born from a disk of gas and dust, shaped by collisions, fed by accretion, rearranged by migrating giants, scarred by impacts, and thinned by exile. It did not become stable because it was always gentle. It became stable after losing enormous amounts of material, after throwing bodies inward, outward, and away, after sorting survivors into rhythms that could last. The Kuiper Belt is not separate from that history. It is one of the places where the history is still visible. Not fully visible. That is important. The Kuiper Belt does not hand us the past in a complete narrative. It gives us fragments, a red surface, a binary orbit, a detached path, a contact shape, a volatile ice plane, a missing population, a comet tail, a faint point of light moving between background stars. Each fragment is small, but together they say something severe. The solar system is less like a finished monument and more like an ancient event still cooling. We live inside the result. Earth feels immediate because it is where our bodies belong. Its sky is bright. Its water moves. Its rocks are warm enough to touch. Its weather is fast enough to frighten us. But much of what made Earth possible may have been decided in cold regions we rarely think about. In the delivery of water, in the distribution of organic chemistry, in the violence and timing of early impacts, in the migration of planets whose gravity altered the entire architecture of the system. The edge is not irrelevant. The edge helped write the center. That is why the Kuiper Belt changes shape in the mind. At first it seems like a place beyond the planets. Then it becomes a ring of leftovers, then a reservoir of comets, then an archive of formation, then a population of worlds, then a set of unsolved gravitational questions, then, finally, something harder to name, a reminder that the familiar solar system is only the visible face of a deeper structure, and the deeper structure is still not fully known. Somewhere beyond Neptune, tonight, there are bodies that have never been named, never been measured, never been seen as more than possible members of a statistical population. They are moving in darkness, not waiting for us, not hiding from us, simply following the sun in silence. Some may be small enough to vanish from every current survey. Some may be large enough to matter, but too dark to notice easily. Some may carry ancient chemistry untouched by warmth. Some may one day be nudged inward, wake under sunlight, and become comets that human beings will mistake for sudden visitors. They will not be sudden. They will have been travelling for millions of years. That is the final discomfort the Kuiper Belt leaves behind. It destroys the human scale of events. A comet in the sky can look like an arrival, but its arrival began before our species had cities. A frozen surface can look unchanged, but radiation has been rewriting it molecule by molecule since before the first life moved in Earth's oceans. An orbit can look like a line in a database, but it may preserve the memory of a planet's migration, a passing star, or a force still unconfirmed. The universe is not hiding its history. It is writing it in a language too slow for instinct. Science is the act of learning to read that slowness, not perfectly, not all at once, not without error, but with enough patience that the blank spaces begin to develop texture. A region once treated as empty becomes populated. A dot becomes Pluto. A tiny contact binary becomes evidence of how worlds assemble. A strange orbit becomes a clue to ancient disturbance. A category collapses and a better one forms. The map does not become less beautiful when it changes. It becomes more honest. And honesty, in space, is rarely comforting. It tells us that home is larger than home feels. It tells us that our star governs bodies so distant that sunlight reaches them as a whisper. It tells us that the substances of life and the engines of destruction may have shared the same frozen reservoirs. It tells us that a world can be small and still important, cold and still active, quiet and still full of history. It tells us that emptiness is often only what complexity looks like before the instruments improve. So if the Kuiper Belt is terrifying, it is not because it is waiting to attack us. It is terrifying because it makes the solar system honest. It removes the clean edge. It takes the comforting diagram and replaces it with a colder image. Billions of ancient bodies circling in the dark, some preserved, some scattered, some paired, some stained red by cosmic rays, some holding clues to the beginning, some carrying paths that no single explanation has yet completely claimed. A vast outer archive, damaged and incomplete, still orbiting the sun that warms our faces. The next time the solar system is drawn as a neat set of planets, ending at Neptune, pause there. Do not let the page fade out. Past that blue planet is not nothing. It is the place where Pluto becomes a member of a crowd, where Arrokoth preserves the gentlest touch of early formation, where Sedna stretches 1 year beyond the memory of civilization, where possible worlds may still wait for proof, where comet seeds sleep until gravity turns them inward, where red ice carries chemistry older than Earth. It is not the end of the solar system. It is the beginning of the part we have barely learned to see. And out there, in sunlight so weak it feels almost forgotten, the frozen witnesses are still moving. They do not need to come closer to matter. They matter because they are there, patient, cold, ancient, and unfinished in our understanding. They are the part of home that still feels like deep space. They are the proof that a familiar star can hold unfamiliar truths at its edge. The map will keep improving, but it will never again be innocent. Once you know the darkness beyond Neptune is crowded, preserved, and still partly unread, the blank margin is gone. What remains is not empty space. It is unfinished knowledge, orbiting